non-normal, we might assume normal, right? So that problem will also be there, right? Otherwise, these three are the very important issues. Inclusion of irrelevant variables, exclusion of important variables, wrong functional form. In fact, this first issue is not very serious, right? The inclusion of irrelevant variable is not a big issue, right? Considered to in relation to the other things, right? In fact, the inclusion of irrelevant variables will make the estimates and the forecast inefficient. But this exclusion of important variables will create a lot of problems. It will make biasness, right, in the estimation, and it will lead to wrong inferences also, right? So unbiasedness and consistency both will get affected if the problem of inclusion of important variables, exclusion of important variable comes. Similarly, wrong functional form. In fact, both can be little compared. Actually, in fact, there is a wonderful discussion of these issues in your Gujarati book, right? So there is a specific chapter on this, and so these three issues, right? Of the three, the last, the later two are very important, and for this we have one important specification test. Known as reset test. Right? I'll just take the particular chapter, and actually that is discussing about the reset test. This is a chapter of Gujarati. Right? So this is again an LM test, mind you. Actually, this reset test is again an LM test. All the LM tests are based on some auxiliary regressions, right? Some auxiliary regressions, right? What they do is they will run the usual regression. They'll run the usual regression. So this is the usual regression. After running the usual regression, they'll take the residual, right? They'll take the residual and they will run an equation on the residuals, mind you. Actually, this is the residual equation. So this is the auxiliary regression. This auxiliary regression will be run, and an LM test will be run. Right? This can be taking a form of chi-square or F test. We will be testing. The null hypothesis would be all the coefficients equal to 0. All the coefficients equal to 0, right? So this test is known as reset test. This was introduced by Ramsey. Right? Now, we will do the test here. Now I had sent the code. You may see the code. Actually, I've forgot to give you the packages required for this test. Right? So have a look at that. If it is not existing, please do it. Actually, I'll give you some time. Right? Download and install it. I'll copy paste the code. Anyway, okay. Here I've taken the data from, actually we are not, no, for this, we're not doing any, we are not taking from our side. So, there is a data no, already given in the code itself. We are going to use that code. So this is the reset test. Okay. Data frame is created with the help of three uh, arrays. You got to know about three uh, uh, vectors: x1, x2, and y. Right? So these are the three vectors. I convert them into one data frame. Right? With the title, actually, this will be looking like your usual CSV file, right? X1, it will have all the values. X2, that column, Y and right is also given. So three column data is given, right? So this data is created, right? Right, we can just run it and see how it looks like. Okay, it is run. Now we can have a look at it. Is saved as DF, right? So we can run it and we can see. Look at that. Just copy and paste how it looks. So this is the data set. Okay. So this is how the data looks like. Three column data set, right? Now we are going to run a model. We are going to run two models, right? This reset test is available in LM test package. This reset test function is available in LM test package, and so we are going to open the library, load the function, so load the package, right? So this is the line. Okay, this is the line which loads the package. Library LM test. Library LM test. So this opens up the package. It is done. It is done. Now we are going to create two variables, y1 and y2. Y1, oh sorry, actually. Oh, okay. Sorry, forget about this one. Actually, see, in fact, reset test starting from here only. Forget about that. Forget about the data, right? Reset test start from here only. We are creating three column: x, y1 and y2, right? X1 is a vector we create. We can see x, how x looks like. We'll see how x looks like. It's a column, right? Numbers from 1 to 30. Numbers from 1 to 30. From that, we are creating two variables. We are creating two variables. One is y1, the other one is y2, right? With some 30 random numbers. 30 random numbers are there. We have random numbers. So we are generating two variables from x1, right? So this is created. We can see this also, right? How it looks like. df x y1 comma y2. Okay, so you have got $30 values. Now we are testing. This is the first model, y1 on x. This is the second model, y2 on x. Right? Here, this is the original y1. But we are modeling y1 as only the function of x. So this model is misspecified, right? Functionally misspecified. What is the original model? This is the original model, right? This model has the polynomial term. This is a quadratic function. But I run the model as a linear model. I run it as linear model, right? So it is misspecified. Second one, y2 is specified as a linear function. This is true. Mind you, this is the original model I used to generate y2. So this is a linear model. This is a quadratic model. So y1 model is specified and y2 model is correctly specified. We can check the retest values for both the things, right? Okay. Now we'll run the model. We'll run the reset test. This is available in LM test package. Just look at this. This is the result. This is the result. Look at that. y1 highly significant. It should not be significant, right? Power 2 reset value is very high. So the model is significantly different from the original model, and so now you have a specification problem, right? You have a specification problem. right? So we know, right? Actually, this reset test clearly says it is highly significant. Pardon? Which value? How much different is it? Ah, how much is it? What about p-value? Huh? What about this one? Y2? Okay. P-value? P-value? Okay, anyway. So with this, you can see, right? To an extent, actually, of course, the p-value here also is 0.01. This also says the model is significant, right? This test is, the test is significant. That null, actually, the supposed to be null model is significant here also, right? At 5% level, right? Since the model, no, the sample is a very small sample, we are getting the results. Otherwise, if it's a bigger sample, we certainly will get p-value. Here it will be high, right? More than 0.05. So it will say this model is not significant. This, this is the model we are talking about. This is the model we are talking about. This model is significant means U2, residual is depending on some variables. Here in this case, variable means the predicted value y hat. Here ui will be taken as the function of all the polynomial values of y hat, right? So if this model, this residual is a function of the x or the predicted y values, naturally we'll say the model is misspecified, right? So if the model is significant, we'll say the model is misspecified. If the model is not significant, right, if all the coefficients are 0, we'll say the model is insignificant and the model is not misspecified, right? That's how we will make a conclusion. Sometimes the value can be why the value you are getting a different value. Why is that you are getting a different value? Random numbers, right? So random numbers are generated with different seed values, right? My computer will be generating differently and your computer will be generating differently. The data will be different later, right? So that is a problem. But anyway, so what we can infer from this is, using this, right, clearly we can say, right, the first model is clearly misspecified. Second model, right, the y2 is little confirming, right? So that's how we can make a conclusion, right? So this is robust, a reset model. Robust regressions are very another interesting topic, right? What is robust regression? Right, you have sometimes the regression, the data are homogeneous. Sometimes the data will have lot of outliers, right? The data might have lot of outliers. I'll just show you one description. I forgot to send that file for you. I am taking the thing from here only. I'll send this one. Right, this passage discusses a lot of issues. Oh, so that the data is for this one. The generated data is for this one. Actually, oh, I missed it. So I have to copying and paste. Okay, is there? Fine, no problem. So robust regression, we are running with some generated data. I am going to generate this data, okay, for robust regression. Right? We can type a df to get the glimpse of the data. Right? This is the robust regression data set. This data set has got an outlier. This data set has got an outlier. If you want to see, we can run it. In fact, this I'll show this file actually because this description clearly indicates, right? If you run a standardized residual and y, right, you get this, right? You have got a outlier in this model, right? Actually, did you see that? Right? If you plot your residuals, right, standardized residuals against the actual y, right, you can see some distinct values there in your data set. Right? Of course, now I'll send you this file. You can take out the codes from that and you can run. Right? All it requires is some packages. It requires to run 2 packages. ggplot, I think actually you have to have a ggplot. Anyway, so it gives you a hint, right, how plot will look like. So in this case, right, if you have random this kind of outliers, if you run your regression model with this data, naturally you will have some bias in your estimation, right? So that will be inconsistent also, right? With this outliers, you will have a inconsistent estimation, right? So for this problem, what you would do is you will run a robust regression. Robust regression, right, will give it's a weighted regression. It's a weighted regression model. It will give low weightage to the values that outlies, right, in your sample points, right, in your data set. The outlier points will be given lesser weights than to the rest of the values, and you will get a consistent regression model, right? So this is the consistent regression model. Consistent regression models are run with the package mass, MASS, with the function RLM, right? Robust linear models, RLM function, right? So this takes care of the problem of outliers, right? So we are going to run that. I am going to run this outliers. In fact, we can compare the OLS and the okay. Look at this value, right? what does it say? What does it say? Right? You are running a regression model. Of course, we have not shown the regression model. Right? We can show the regression models also. Both the regression model we can show. Right? Summary. OLS. We can compare these two values to two models. One is the OLS model and the robust regression model. The t-values have significantly improved, mind you. For two things, t-values have improved, and the standard errors, right? Actually, the standard errors are reduced. The standard errors are reduced. You know why? Usually, all the standard errors, the coefficients, standard errors are determined by the variance of the residuals, right? Or the standard error of the residuals, or variance as a standard deviation of the residuals will play an important role in determining the standard errors of the individual coefficients, right? To see that actually it will look like the standard errors, all the standard errors of the coefficients are in proportion standard deviation of the residuals, right? So this is we can see that from the formula of standard errors of individual coefficients. So naturally, this robust standard error reduces the residual standard deviation, right? Actually, you can look at that. Look at this. In the OLS model, in the OLS model, standard deviation is 49, right? In the robust model, the standard deviation is 0.9. That's why the standard error is reduced in the robust model, right? Then that will give the very robust results compared to the OLS models, right? So this is robust regression models. Whatever you see, right, in your Gujarati book, you can work out, right? That is the point we want to make, right? In fact, Gujarati has used a lot of softwares, right, to demonstrate the concepts, right? But R can do everything, right, at one go, right? So this is standard, robust regression model, right? Then we'll move on to the next exercise. Normality test. This is very important issue, right? Running a normality test, right? So most of the time, CLRM, classical linear regression models, right, using a lot of tests. Most of them assume the model, population is normal. Population is normal, and the variable we use are normal, right? Including the residual variables, right? The residuals we assume them as normal, right? So what we need to do now is, right, before doing any regression, so any inferential analysis, we have to check whether your residual is normal or not, right? Very prominent, actually, of course, no 2-3 normality tests are there, right? In SPSS, we can have QQ plot, right, based on the cumulative distributions, right? Normal cumulative distributions will be there, right? The cumulative distribution of the variables in your model, right? Actual distribution, cumulative distribution of your model will be taken and both will be compared, right? Whether they follow that pattern. That is a visual test. QQ plot is a visual test. Some statistical tests are also available. We all know, right? Actually, this normal distribution will have a distributional characteristics. Distributional characteristics. For example, skewness and kurtosis, right? Skewness will be, I hope, 0. Kurtosis is 3, right? Skewness is 0 and kurtosis is 3, right? So it will compare those characteristics, skewness and kurtosis, right? So this Jarbara test, actually your EViews is running that test only, Jarbara test, right? The Jarbara test is based on the skewness and kurtosis of the normal distribution, right? So your actual values, the variable will be taken, and the skewness and kurtosis of that variable will be tested against the normal, the skewness and kurtosis of the normal distribution, right? 0 and 3, right? So comparing that, it will confirm the statistical test. It will give the statistical test result. Okay. So it can be run with your T series package. Right? There is a package called T series. Right? You may have to install T series package. Get this point? T series. Right? You have to install T series package to run this test. In that T series, you have a function called jar.bera.test. For that, you have to give the residual values, right? Residual values from your OLS model, right? Here, I have not specified anything. Actually, in fact, I wrote, but I went off. I'll write again, right? It's very simple. I'll read the data. Actually, I've sent you the data, SLRM, right? You can open the SLRM data and you can run. I'll use this data. I'll read the data. Read CSV, SLRM. SLRM. I'm going to read slrm.csv, right? And from that data, I'm going to run the OLS. LM is a OLS model. I don't know, I'm not very sure whether the variables are written in capital or small letter. Let me check the data set. capital letter, right? I can use capital letter. This is a consumption function. This is a consumption function taken. This data is taken from your Gujarati data, Gujarati book. So let me write y tilde 1 plus x comma data equal to data. I'm going to run this model. Let me check. It is saying data is not available. Oh, it is taking something else. Right? This problem will come. So in that case, I have to clear that off. I should clear the data from the work. So how would you do it? Remove list ls. So I've removed everything. Now I should not have anything, right? I don't have any data on data. Now let me rerun. Okay. Now I am getting the results for Jarbara. Jarbara test null hypothesis is normal distribution. Print the result. For result is okay. Is there la? Yeah. The result has come. Maybe we have to write summary of results. Why sometimes we have to type summary, sometimes print, because of the property of the list object generated. Sometimes the list object is of S3 kind. Sometimes the list object, the output, I'm telling, the output object will be of S3 kind, right? S3 kind is usually I think is typed as print. It can be displayed with print command. S4 objects are typed with summary command, right? So slight difference is there. Okay, now the result has come, right? I'll just show you the result. This consumption function is not the actual data, it was a generated data. must be a nice data. Actually, you should have the nice results, theoretical results. Just look at that. The residual is normal, right? P is insignificant. P is insignificant. That means it confirms the null hypothesis. It confirms the null hypothesis. That means your residual is completely normal, right? Completely normal, right? Natural. Actually, that's what we can anticipate, right? So, theoretically generated data, and so it must be a normal data, right? Actually, so it is showing that it is confirming. Okay, fine. Okay. So I've talked all the things about specification things, right? Now we'll move on to the two important models, right? One is, in fact, Professor Santosh told me to talk to you about the ANOVA and COVA models, right? ANOVA and COVA models. I think it is a very simple model, right? So I don't think we should spend time on that. But anyway, I'll just talk about the nuances of the ANOVA model, right? I have one data. I know I have. It is a OLS model only, right? You do not have to worry too much about that. There are two types of qualitative models. Broadly, qualitative model are of two types. Qualitative variable models are of two types. Right? What are all they? Models with quality variables as independent variables. Right? This is one type. Models with quality variables as independent variables. Second type is models quality variables as dependent variables. Right? We all know, right? There are two types of models that comes under this one. Very prominent models that comes under this type. One is ANOVA model. The other one is ANCOVA model. Right? ANOVA and ANCOVA models. Right? So these ANOVA and ANCOVA models take the quality variables as independent variables. Right? So you will have the quality variables on the right hand side of the regression equation. Right? There are other types. Quality variables as dependent variable. Right? So here you will have probate, logit models. Right? Of course, you will have different variants of this. Right? You have multinomial, binomial logit probate and multinomial logit probate. Right? Ordered logit probate. Right? Everything is there. Some variants of it. So these are the two prominent things. In this one, actually, of late people don't call them quality variables, right? Sometimes they say limited variables, limited variables. Instead of calling them qualitative variables, they call them limited variables, right? So sometimes the whole range of the variables will not be taken. In fact, this dependent variable sometimes will take a very limited range values, right? In this, there are two more models, right? One is censored models. Truncated models, right? So regression models can be classified broadly into models with qualitative variables as independent variables, qualitative variables as dependent variables. This, the scope of it is a little expanded to include limited variables. Sometimes, the y will not take the whole range of values. I'll tell you the context, right? In those contexts, right, some models are generated. Actually, of late, people talk about censored and truncated models. Truncated models, right? So we discuss, right, in this demonstration about these models only: probit, logit, and censored regression model. Truncated, no, I'm not going to cover, right? Under censored model, we'll be talking about 2-bit models, right? 2-bit models. So this is what we are going to discuss about, right? I'll give a brief introduction about ANOVA and UNCOVA models, right? First, I'll talk about that, but I'm not going to run any models, right, using R. I'm just going to tell you because Santosh was asking, right? Give an introduction about UNCOVA models, ANOVA models. Right? I'll just talk about that. Qualitative variables, otherwise known as dummy variable models, right? They can be called indicator variable models, binary variable models, qualitative models, dichotomous models, and factor variable models, right? There are two codings, right, in the converting the variables, right? We will convert the factor variables with codings, right? Sometimes we use 0, 1 codes, or sometimes we use -1 and +1 codes, right? So, but in economics purpose, right, in economic models, we'll be mostly using 0, 1 codes, presence and absence, 0 and 1, right? Fine. What is the implication of this model? Actually, in fact, if there are only two categories, quantity means categorical variables. If there are only two categories, we can code them 0, 1, right? If there are multi-category models, right? Sometimes you'll have in this case region, 4 categories, right? How would you code this, right? You have to code them 0, 1 only, right? How would you code? You will take each of the categories as one dummy variable, right? So we'll make, if it has got 4 categories, we'll make 4 dummy variables, 0, 1 nature, right? So if the region is having 4 category region, right, you will convert them into 4 dummy variables, right? Each of it is having 0, 1 indication, right? If a particular thing is present in a particular employee is present in north, we'll say if the person belongs to north, I'll put 1, otherwise I'll put 0, right? Like that for each of the dummies, I can code 0, 1. You can code that with 0, 1, right? So you can do that like this. And So dummy variable models will have a problem of dummy variable trap, right? Ideally, if you are having 4 category dummy variables, you can at the most generate 3 dummy variables, right? Only 3 variables can be used in your regression model simultaneously, right? You should not use all the 4 variables, right? So this is known as dummy variable trap, right? You should not get into dummy variable trap. To avoid the dummy variable trap, right? If there is 4 categories, you have to use at the most 3 dummy variables corresponding to 3 categories, right? Okay. If you want to use all the 4, then in the regression model you have to drop the intercept term. Of course, the meaning would change, right? So dummy variables will have a different meaning from compared to the other usual regression models. Usual regression models, right? The coefficients will have the meaning of marginality, right? So it will indicate the marginal increase or decrease, marginal change. The coefficients will indicate marginal change. But in this dummy variable, right, the meaning of the coefficients will be completely different. It will show the mean difference, differences in means, right? What is the differences in means? Right here, this coefficients will indicate the difference in averages of categories. Differences in averages of categories. I'll just take one example and let you know. Yeah. This is a salary model, wage model, right? Y is the wage, D is the education level of the workers. Education level of the workers. If the worker is literate, I'll give him 1. Otherwise, I'll give 0. If the person is literate, I'll give 1. Otherwise, I'll give 0. If I run this model, what would the beta indicate? The beta would indicate one important thing. As I told you, this will indicate the differences in average. What is the differences in average? You have 2 categories. One is literates, the other one is illiterates, right? Salary of the average salary of the literates is one average. Average salary of the illiterate employees is another average. The difference, right? The difference between the 2 averages is indicated by this beta, right? What would the alpha indicate? Alpha would indicate the average of the left out category. Average of the left out category, right? Let us take this case. We have 2 categories here, right? Illiterates and literates. The dummy indicates the literates category, right? If it is 1, literate, otherwise 0, right? What variable is dropped here? Right? One more dummy is possible. Illiterates, right? Illiterate dummy will indicate 1 if it is an illiterate employee, 0 if he is not a illiterate employee, right? So that variable is dropped. That category is dropped, right? We will call it base category. We will call it base category, right? So this average, this alpha is the average of the base category. Means what? The average salary of the illiterate employee. Get this point clear? So alpha is the average salary of the illiterate employee, right? Beta is the mean, the differences in the averages of the illiterate and illiterate employees, right? Otherwise, the premium, right, salary the literate employee gets is reflected in the beta, right? So this is how the beta should be interpreted. This is the mean difference, right? In fact, these models are, can be little expanded, right? If it is a two-category model, it is like this, right? If it is a multi-category model, right, the thing is little expanded. Let's take this case. I've introduced two dummies. I've introduced two dummies here, right? So salary, first dummy is for school, employee who had completed school. Second dummy is the dummy for graduate employees, right? So third one could be illiterates again. Illiterates, school going and school completed and college completed employees, right? Then what would be the beta 1? Beta 1 is the premium salary of the school gone employee over and above the illiterate employee. Beta 2 is the premium salary of the college going employee over and above the base category, right? The illiterate employee. Get this point clear? So like this we can remodel, right? One more category, actually one more type of typology is, this is, so two different dummy variables can also be included, two different dummies. Yeah, model 3. D1 is the gender dummy, right? D1 is the gender dummy. D2 is the education dummy, right? We can use that also. We can use gender dummy and education dummy, right? We can use different dummy variable. Actually, different. We can introduce the dummy variables in separate form and in the multiplication form also, right? Here, this alpha now would represent the salary of the double disadvantaged employees. Female, right? If I included male dummy, what is the excluded category here? Female, right? What is the dummy here? Illiterate employee. Illiterate female is the base category. Get this point clear? Double excluded, right? Illiterate female employee of the is the base category, right? So alpha would represent the illiterate, the salary of the average salary of the illiterate female employees, right? This beta 3 will talk about the double advantaged employees, right? Literate male employees, the premium salary of the literate male employees, right? So this is how the average is decomposed. The average is decomposed in these models, right? So these models have got distinct advantage over the traditional T and F tests, because we were talking about pure dummy variable models, right? All the three models are talking about all the independent variables as dummy variables. We can have a mixed models also, right? We can mix the dummy variables with the regular quantitative variables, right? Those models are known as ANCOVA models, right? Those models are known as ANCOVA models. In fact, in the ANCOVA models, the primary concern is regarding these average salaries only, the averages only, the differences in averages, right? Our concern and our analysis is about these averages only, right? In this determination, we can do some controlling also, right? In the controlling, when we are finding the average differences in averages, we can do some controlling. I'll just give you one example, right? We know, right? Actually, we are studying the labor markets, right? We are studying the labor markets, right? In the labor markets, male are paid higher than female, right? Male are paid on an average higher than the females, right? The differences, sometimes people would ask whether the differences can be taken as the uh, discrimination, whether these differences can be taken as a discrimination, right? People would say it doesn't matter male or female, right? Labor market is pure. It offers wage according to their ability or according to their educational status, right? If all the males are better educated than the females, right? On an average, not all, on an average, if the male employees are better educated than the female employees, the differences are sometimes due to the differences in their educational level, right? So you cannot attribute the entire difference as the discrimination. So what should you do? Now you should, to confirm whether the social discrimination really exists, you should control for the effect of education, right? So ANOVA models are usually used in this context, right, to eliminate the other variates from the discussion of mean difference analysis, right? So in that cases, right, these ANCOVA models are very famous, right? So on the whole, these ANCOVA models are better than most of the usual statistical tests, right? In fact, controlling, right, controlling and finding the differences after controlling, right? This controlling thing, really is quite common in the natural sciences, but in social sciences, controlling cannot be done, right, on the experimental basis, right? It cannot be done anyway, right, like in your natural sciences. So naturally, right, in econometrics, the controlling is done with the inclusion of additional controlling variables, right? You cannot do the actual control, right? You will control after collecting the data. You will introduce additional variables in the regression model, right? That is equivalent to controlling in the natural science parlance, right? So these ANCOVA models are a very good example of how effectively, right, we are matching with the methodology of the natural sciences with this controlling variables, right? So these models are very famous, right, in that context. So ANCOVA models and ANOVA models are not like the models we are using in the regular regression models, right? So regular regression models are little different, and this ANCOVA and ANOVA models are different. In fact, we can say the advantages of this model in multiple ways. These models are have acute advantages, right? It is better than your t-test. Why is it better than t-test? T-test can only compare two averages, but here you are comparing two conditional averages, right? Conditioned averages, right? Secondly, your f-test can only compare the it can only say whether population is homogeneous or not. It will not say which group is different from another group, right? If there are three groups, it can only say, right, all the three are not same. Sometimes first group and second group may be different, and first group and third group may be same, right? There could be a lot of possibilities. All those things can be analyzed with this ANOVA and ANCOVA models, and it has got varied applications, right? Actually, I have, let us not go deep into them, right? So ANOVA and ANCOVA models are very useful models for our purpose. So comparing, this is a better model than f-test, better model than t-test. What else? Structural breaks can be easily identified with this. Chow. This is better than chow test. anyway, I'm going to know if I get the time, I'll talk about the chow test also. Better than chow test, right? The chow test can only say whether the true period is different, right? This models, right? ANOVA models can say, right, whether they are different by the intercept, whether they are different by their slope, whether both are different, right? All those things can be very in a detailed way we can distinguish. We can study the interaction effect, right? We can study the interaction effect, and we can remove the seasonal effects using this ANCOVA models, right? So it has got a lot of advantages. It has got a lot of advantages. Kingsley regression models are estimated with this ANCOVA models. Kingsley regressions, right? We know the importance of Kingsley regression models in our market analysis, right? These models are estimated with these ANCOVA models only, right? So panel data regressions are based on this ANOVA model, right? Okay, so this is what ANOVA is good about ANOVA and ANCOVA models, right? You can use your usual OLS to estimate all this. Now I am going to discuss about the probit and logic models. Quickly, I'll talk about the probit and the logic models. Dummy variables as dependent variables, right? Sometimes the outcome variables become a dummy variable, right? There are a lot of situations where you can anticipate this one, right? Buying choice models, right? What influences a person to buy a product, right, is a very interesting question, right? What makes a person to buy, right? As a manager, we'll be interested to know all this, right? Similarly, a banker would like to know why some people are paying back and some people are not able to pay back, right? How would I know, right? From his characteristics, the probability of that person paying back, right? I may be interested to know all this, right? So these are the few situations where we are like to have a binary dependent variable, right? Models, right? So in this model, there are two prominent models exist. One is probit, the other one is logit. Of course, earlier there used to be some model called linear probability models, right? These models suffers from multiple problems, and so in this binary outcome models, right? This probit and logit models are very famous, right? So first we'll go one by one, right? We'll study the logic model first, right? Logic models, right? What does this logic model say? Right, logic model, interestingly, specified as this. Actually, I'll just write the specification of the logic model. In logic model, logic is taken as the function of the logic model. The dependent variable, right, is converted into the 0 1s are converted into logits. What is logit? Logit is nothing but log of odds. log of odds, right? So for each of the zeros or ones, we'll calculate the logit values, and it will be taken as the y variable, right? Against that, the independent variables are regressed, right? Against it, the independent variables are regressed. Okay, so this is the regression model, right? This is not a wireless model. This is a maximum likelihood estimator model, right? So MLE model, right? So this model should be interpreted this way. I'll just let us take how would you interpret the coefficients. That is very, very important. Okay. Okay, so this is the logit. This is the LPM. This is the LPM with small link function. With the small link function, we will take like this. Beta is a marginal value. Beta is a marginal value. Beta is a marginal change when there is a small change in x. So beta measures the marginal change in logit when there is a unit change in x. Marginal change in logit. How would you interpret it? How would you interpret? Right? Log of odds. Log of odds. Right? Odds means what? Probability ratio. Probability of success, right? Over probability of failure. Probability of failure. Right? Intuitively, the logit measures, right? Otherwise, odds ratio measures the probability of success in relation to the failure. Right? Forget about the failure. Right? It is measuring about, it is measuring the probability of success. Log of that probability is again some monotonic function of probability only. So what you can do is some measure of probability of success. Odds ratio is nothing but some measure of probability of success. Log of odds is also some measure of probability of success. Some measure of probability of success. So beta is nothing but probability of success, right? When there is a unit change in x, right? This is how the odds ratio will be interpreted. The beta will be interpreted in the logit model, right? The only thing is this is beta is log of odds, right? If you want to see the odds, right? Actually, you have to take the exponential. That is the anti-log, right? Exponential is the anti-log value, right? So you have to take anti-log of beta to find the odds ratio value, right? So to convert the logit into odds ratio, you have to take the exponential value, right? So in the logit model, you will have the beta value. If you take the exponential of the beta value, you will get the odds ratio, right? That can be very easily interpreted intuitively, right? As I told you, right? Odds ratio is nothing but some measure of probability of success. Some measure of probability of success, right? Marginal change means how does it change, right? Is it increasing or decreasing? If it is positive, you will say it is increasing. If it is negative, you will say it is decreasing. Like that, you can interpret, right? So this interpretation part is very, very important in the logit model, right? As I told you, right? This is a regular regression model, but this probit is little different. Probit is little different, right? Probit, you run a regression model, right? There you will see the link function, right? Some link function you use, right? In that model, the alphas and betas are some z value, right? Some z value, some z value, some z score. In fact, these z scores are some pi. Pi of z is the cumulative normal function. Right? So cumulative normal function is derived, cumulative probability of success is derived from some function of z, some function of z. I've told pi, but it can be taken as some function of z, right? So you can derive the z value. You can derive the cumulative normal probability using this z, right? So the probability is not directly interpretable in the probit model, right? So you have to convert this z into probability with some functions, right? And so probability, actually this probit models, right, you won't be able to interpret beta straight away, marginal values straight away, right? And so because of this reason, logic models are intuitively used most of the times, right? But anyway, actually you can convert, right? There is a conversion functions, right? Using the conversion functions, you can estimate the value of beta into normal marginal probabilities. You can convert, you can compute the marginal probabilities using this beta value, right? So this is what you should know about this logit and probit, right? This theory is very important, right? I'm going to run this model. To understand this, you should know all this, right? I'll give you some description about the data set. So this is the probit model. I'll share this data with you. I'll share this, I'll share this file with you, right? This discusses about this data set that I'm going to use. This is about admission data. This is about an admission data, right? In the European context, right? There are how many variables? 4 variables. There are 4 variables in your data set. One is whether the details about the admission status of the student, the grade of the students, GPA of the students, rank of the student, right? So 4 variables are given, right? We are trying to determine what determines the admission chances of the students. What determine the admission chances of the students, right? This is the model that I'm going to discuss, right? I have given the data set also, binary data set, right? We know the binary data set. What is the binary set? This is the binary data set, right? This is the binary data set, right? So I'm going to feed the data. I'm going to feed the data into R. For this model, I require the following packages, right? Some of it we have already installed in your R. Some of it you have not. MFX is a package. We require MFX package. We require sandwich package. We have already installed in your computer, and we need beta reg, beta reg, beta reg, BETA-REG, beta reg. So these three packages you require to run this logit and probit models. Of course, MFX and all these three packages are required for our probit models, right? To convert the coefficients into this marginal values, right? Anyway, so I've installed all these packages. Before that, I want to clear all the data. What is that I want to do? First, remove list equal to ls. Yes. Right, all the workspace is cleared off. Right, workspace is cleared off.
So comfortably, if you complete before breaking itself, we can give that. I will ask them. I will share the question. So I will ask them
Okay.
to do it. And because
You want to
after
finish
that,
it?
after that, people may get late. As we that they may not come.
Okay. You want to finish it now itself?
And comfortably, it's
Oh, yeah. Okay, so I have a library. I'm going to open. Already I've installed these packages, right? So I'm going to now open it. It is done. Everything is done. For me, everything is done. Anyway, now I'm going to open the binary data. Right? I have the data with me. So I'm going to run it. It is open now. Right? Here, we have to define the variables as factor variables. Right? Some of it are factor variables. It cannot be run the way as our quantitative variables, scale variables, right? Here, the rank is not the quantitative variable. Rank here is the qualitative variable, right? It is taken as a qualitative variable here. So I am going to convert, right, in the data 1, right, this particular column, data 1 rank column. Rank column has to be taken as a factor variable, right? I am defining it, right? R has to instruct, right, this factor variable as factor separately, right? It is done. Now I am going to run the probit model, right? I am going to run the probits. So probit model is run, right? So I'll just show the probit model. So this is the probit model, right? Probit models are run with GLM function, which is available in our base package, right? Our base package has got GLM function, right? It is run with that GLM function, right? We have to specify the link function as logit. That's it. So it is available, right? Just look at this. This is run with GLM function only. Actually, all ANOVA also know run with the GLM functions. So it is like running all the qualitative models with the GLM only. So admit is the dependent variable, right? Grade, GPA, rank as independent variables. Link variable is probit. Binomial link probit. right? Our usual data, right? With this specification, I was able to run the probit model. Now the probit model is estimated, and I am trying to get the summary of this probit model. Right after this, right, as I told you, this beta is not, these coefficients are not directly interpretable. I've told you it can only show whether they are positively related or negatively related, right? So now we can only say rank 2 3 means, no, okay, we can see the data set. What is this first category, rank category, first category, second category, third category, all are explained here. Let me check what is this rank variable all about. Rank takes on the values 1 through 4. Rank 1 is the highest percentile, while those of rank 4 have the lowest. Right? The percentile values, right, is taken. So in fact, admission capability, the admission, right, is compared for one group against the other. Actually, it's like, ANOVA model. Actually, sorry, ANCOVA model, right? Remaining them, right? This rank variable is a qualitative variable, right? We are taking 3 categories, right? Maybe the first category will be the least one, and all the remaining categories will be taken. Actually, I think that is taken as the base category, right? Let's see how I get the. Now we can see the results. Yeah, rank 2, rank 3, rank 4. In relation to the first category, right? Top percentile students, what is the chance for second category students, third category, and fourth category? So the base is top ranking students, right? So, right, in relation to them, right, their chances are less, right? In relation to the first category students, the chances are less. Like that, you should interpret. The values are increasing, right? The chances, the negative chances are increasing, right? So this is how it should be interpreted. But you cannot interpret it straight away, right? You have to convert this into a marginal probability values. Marginal probability values that alone can be interpreted straight away, right? So now let's see how we do that. So marginal effects we can estimate with MFX package, right? Function named probit MFX. Probit MFX. This is the function, right? With this function we can calculate the marginal effects, right? This function is available in MFX package, right? This is the detail I'm giving. This is the argument I'm passing, right? So I'm going to run this one. Now let's see. So the value has come. This is the marginal value. We'll interpret this. Look at this. When there is 1 unit change in the grade point, the marginal probability of getting admission increases by 0.0004 units. The probability increases by this many units. When GPA increases by 1 unit, the probability of getting admission increases by 1.66 units, right? So compared to the top ranking students, the probability of getting admitted is is declining, right? So this is how it should be interpreted. This is marginal effects, probability, straight probability. Okay, fine. So to calculate this, you have to require a separate function for that. Now let us run the logit. Logit also run with the GLM functions, but here the link function would be logit instead of probit. Just look at this. Logit. So this is it. This is what the link function. So after giving it, you can get the log function. Sorry, logit model. You can run the logit model. Now let me run the logit model. As we calculate the marginal values in your probit, you have to calculate the odds ratio. Right? I'll just tell you. This is the model. One good thing about SPSS is SPSS will give both. It will give the logit values and it will give the odds ratio also. Exponential of logit also it will give. But in this case, we have to calculate. This gives you the logit values. From the logit value, you have to find the odds ratio. Look at this. So this is the logit model, right? So as in the case of probit, here also you can interpret the relationship, whether they are positively related or they are negatively related, that can be interpreted, right? So all the values are significant, right, at 5% level, right? So here also the values are positively related for these two scale variables, and for the other categorical categories, dummy variables, the relationship is negative, right? Okay. So this is what is given. Now let us take the odds ratio, right? How would you take the odds ratio? If you take the exponential values of this logit values, you will get the odds ratio. That will give you the intuitive interpretation. That will give the intuitive meaning, right? So let me run it to get this. Yeah, it has come. Just look at this. Log of odds. Log of, actually, see, this is odds, right? The odds for a person, right? If the grade increases by 1 unit, the odds of that person getting admitted increases by 0.0022670. Increases by, right, this much units, right? If the GPA increases by 1 unit, the odds of that person, right, getting admitted, right, increases twofold, right? Increases twofold. That's what it says. 2.23 times, right, increases, right? If that person belongs to second percentile, right, second category percentile, the odds decreases by 0.5 unit, right, 0.5, right? If the first person has the odd of winning 1, the second category odd of winning is 0.5. Third category people, the odds of winning is 0.26. Fourth category people, the odds of winning is 1/5. half, 1/4, 1/5, right? Like that you can interpret, right? So odds can be interpreted intuitively as we interpret our marginal probabilities, right? So this is how these values could be estimated with R, right? We'll talk about, we will stop here. If any question, there, I'll just try to explain. Otherwise, we will discuss about Tobit in the post-lunch session, right? Gujarati does not have a good discussion about this logic probit models, right? That is the biggest complaint against that book, right? It doesn't have a good discussion, right? Even for this Tobit, it does not have a good point to make, right? The discussion was not that clear, right? So we could not take data from there, right?